AP Calculus BC, Unit 3 review, corrective, to help you get ready for your retest. So hopefully you've tried it. I'm going to go ahead and go over it and go over the answers. So mean value theorem, state the theorem. I guess it's just, do you know what the mean value theorem is? If f of x is continuous, on a closed interval and differentiable on the open interval, then there is at least one point C where C is between A and B, but not including the endpoints, and where f prime at C equals f of B minus f of A over B minus A, which is also the way we find f prime average. So this is mean value theorem for derivatives. Okay, so on problem 2, I guess we're going to go ahead and use this. Find all C's as guaranteed by the mean value theorem for derivatives for this function. So the first thing you need to do is find the actual, well, one of the things you have to do is find the actual derivative, right? And then the other thing is we need to find the average mean value of the derivative. And so that's going to be f of 3 minus f of 1 over 3 minus 1. It's good to show your setup. And if we plug 3 into this, you get 27 minus 27 is 0. And you plug 1 in, and you get 1 minus 3 is negative 2. And so we get average slope is 1. And so then we set the actual derivative equal to the average derivative to find the places where the actual derivative equals the average derivative, which is the guarantee of the mean value theorem. So we get a quadratic trinomial. We try and factor it. Factor is not going to work. It's prime. That doesn't mean it doesn't have answers. So we're going to use quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. So it's going to be positive 6 plus or minus the square root of 36 plus 12 is 48. And we could take a 16 out of that. So 6 plus or minus 4 root 3 over 6. So we get we could take a 2 out of everything in the top and everything on the bottom. So 3 plus or minus 2 root 3 over 3. So one of the answers is 3 plus 2 root 3. And one of them is 3 minus 2 root 3. But we need to make sure they're between 1 and 3. So I'm going to estimate these. Root 3 is about 1.7. It's between square root of 1 and square root of 4, between 1 and 2. So I'm going to say about 1.7. So it's about 3.4. So this is like negative 0.4 over 3. And then this is going to be about 6.4 over 3. This one's out because it's negative. It's got to be between 1 and 3. This is like a 2.1 or something like that. So that one's good. So the C value is 3 plus 2 root 3 over 3. So algebraically, you might get more values than you're allowed to use because they end up falling outside the endpoints or on the endpoints. So there you go. Okay, optimization. I have a couple challenging optimization problems here for you. Problems that we've done, similar problems back in Calc AV. This was, some of you guys chose this as your optimization project last year, right? The box. So let's see, 24 by 36 sheet of cardboard is folded in half to form a 24 by 18. So this is going to be 18 from here to here, right? 24 by 18. So one part's going to be the lid, one part's going to be the base. Then 4 congruent squares of side length x are cut from the corners of the folded rectangle. The sheet is unfolded. The 6 tabs are folded up to form a box with the sides and lid. Find the maximum volume of the value of x. That gives it the maximum volume. Okay. So our limitation here is the amount of material we have. And so we've got to cut these corners out. So we're trying to maximize volume. So we got to come up with a formula for the volume here. And I'm going to create a variable for the size of the corners because that's going to change. I'm trying to find the value that it says x. Okay, so x is already on there. So we're trying to find the sizes of these corners that we need to cut out to maximize our volume with this set amount of material. And we're going to end up throwing away the material that we cut out. So the volume is, I mean, you could draw a picture of this. You know, it kind of looks like that. So the height of the whole thing is 2x, right? And then this length right here. So this is going to be, this length right here is going to be 18 minus 2x. And then this length is going to be 24 minus 2x. So there we go. We have our volume formula. We could simplify it, you know, probably might want to. Might like the factored version for something else later on. So we're going to have to FOIL this out. So we got to distribute. So what's 18 times 24? 8 times 4 is 32. Carry the 3. 16, 19, 0, 4, 2, 2, 13. Carry the 1. 432. 432. Minus 36x, right? Minus 36x minus 48x plus 4x squared. And so then we could distribute this in and maybe write it in more of a standard form. So there's a 8x cubed first, and then minus 70, 84, 184 times 2, 168x squared minus 864x. So yeah, there we go. I mean, we could try and factor the biggest number out of everything possible. And if we did that earlier, it might have been easier, but we could take at least a 2 out of everything. Half that's going to be 84. Yeah, I think we take a 4 out of everything. That would leave you with 2x cubed, 84, 42x squared, 432, 216x. Ooh, and we could take another 2 out. So I'm doing this right now, and we can do this later. Okay, I think that's as far as we can go. Anyways, I might use this in my table. You could use this, you could use this. But we got to find critical points and endpoints. So we're going to do v prime equals, and we can just leave this one. The 8 is out front. We don't need to do product rule. Inside is 3x squared minus 42x minus 108. And we're going to set that equal to 0 undefined. And then we would want to factor this. Now, can we take a 3 out of all these? That, you know, that trick when we add up all the digits, 4 plus 2 is 6, 3 goes into 6, 1 plus 0 plus 8 is 9, 3 goes into 9. So I could take a 3 out of everything. And this 8 shouldn't disappear. That's part of the derivative. So what's that going to be? 14 minus 36. That makes it a little easier for whatever we're going to do next. Now, you could try and factor this. But 6 and 6 is 12, 4 and 9 is 13, 2 and 18 is 20, 1 and 36 is 35. So we're not, I don't think it's going to work. We're going to have to use quadratic formula again. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's going to be positive 14 plus or minus 14 squared. Is that 256? 16, carry the 1. 4 is 5, 0, 4, 1, 6, 9, 196. So that's 196 plus 72, 144. And so then that's going to be 340. So, oh wait, hold on a second. Did I make a mistake somewhere? Ooh, oh no. I think I made a mistake. That's positive, and I made it negative. That should be positive, 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 this should be positive, this should be negative. So that's going to make it 196 minus 144, 52. Well, take a 4 out of it. 4 times 13. So 14 plus or minus 2 square root 13 over 2. 7 plus or minus root 13. So one of them is 7 plus root 13. The other one's 7 minus root 13. So estimates without a calculator, square root 13 is between 9 and 16. So it's between 3 and 4. It's a lot closer to 16 than 9. It's 3 away from 16, 4 away from 9. So really about 3.6. This will be about 10.6. This will be about 3.4. Okay. So, I mean, these are your critical points. Now, we might throw one away if it's outside the endpoints. So that's probably the next thing we should do is figure out what the endpoints are. And so the endpoints for x, could x be 0? Sure, it'd be a flat box, right? X could be 0. What's the biggest x could be? Well, that would be if it just took up the whole side. So it's either 12 or 9. Well, 9's more restrictive, right? So if it took up that whole side right there, x and x, they would split the 18 and you would get 9, right? Here you get 12, but then that makes this side end up with like negative dimensions. So those are your endpoints. So then we're going to make a table as much as possible, use extreme value theorem. I think there's no problem I'm going to give you that we can't. So then we'll entertain other options in those cases. So 0, 7 minus the square root of 13, and then 9, 7 plus the square root of 13 is outside the endpoints. So we're not going to do that one. So we plug this into volume. Now, I personally, I don't know. I mean, it might be, this is going to be messy no matter what. And this is something where I'd probably like use a calculator to do it. But if you plug 0 in, I mean, the volume is going to be 0. If you plug 9 in, I think that was the other extreme case, you're going to get a 0 there, and the whole volume is going to go to 0. So those two are easy. This one's going to be kind of messy because you'd have to plug this into this equation. So, I mean, it's going to be 7 minus root 13 cubed minus 21, 7 minus root 13 squared plus 108, 7 minus root 13. So this is going to be ugly. Like, I'm pretty sure it's going to be a positive. It should come out as a positive number. But where's my graphing calculator? So, you don't need a graphing calculator. You can do scientific, but let's just see what this is. And we'll talk about, well, what if you didn't have a calculator? You could just assume that comes out positive, so it's the max. Otherwise, the max would be the edges. But let's see. Easiest way I think to do this is do 7 minus the square root of 13. Get that answer, and then do 8 times parentheses the answer raised to the third power minus 21 times the answer squared plus 108 times the answer, close parentheses, and we get 1309.954. So that's the max. So this is EVT. So that's your max. These are your mins, tied for the min. Minimum volume is 0. Now that was kind of challenging. So the other option is, well, what if I don't feel comfortable with that and I don't have a calculator? Well, we could try and use first derivative test, but it doesn't always work. 2, it's a lot harder to explain. So we can do a line check with this. So we have we have 2 critical points, right? We have 7 minus the square root of 13, and we have 7 plus the square root of 13. And if you were to test a point, x equals 0, seems like a nice easy one. If you plug 0 in here, you get a positive, and then negative, and then positive. So it's going up, it's going down, it's going up. Now, with just this information, I cannot conclude a max or a min because this goes up forever. Does it go higher than this? You have to know the endpoints. So the endpoints are 0 and 9. And so in this situation, okay, this is a relative max. This is a relative min right here. But because it's the only relative max, the only, relative extrema critical point between the endpoints, and we could say, well, that's for sure the max because it just goes down on the sides to where the ends are. So, this would end up being an absolute max if you consider the endpoints. You wouldn't know what the max value was. So, you could say we can start with this. The volume has a relative, so you got to justify the relative max or min first if you can do first derivative test. The volume has a relative maximum at x equals 7 minus root 13 units are inches by the first derivative test for relative extrema, since v prime is positive for x less than 7 minus root 13, and v prime is negative for 7 root 13 x to 7 plus root 13. So that's just justifying the relative max, which is what you would need to do if you're going to do first derivative. Now you got to tell me why it's an absolute max. Since this is the only relative extrema on 0 to 9, it must be an absolute maximum. I mean, this is what you got to do if you're not going to use EVT. You do EVT, you say the relative, the absolute max is 1309.954 inches cubed, by the way, when x equals 7 minus root 3 inches. By extreme value theorem, checking in points, critical points. That's a lot easier to defend, but without a calculator, that number was a little harder to really prove. All right, so we have a business problem here. Let's see. Okay, so R is for revenue, right? C is for cost. X measures thousands of units, which you make sure you reflect in your answer. And is there a production level that maximizes profit? So we need a profit function. Profit is revenue minus cost. And so in this case, revenue was 8 square root x. Sometimes they give you the price, and so revenue would be price times quantity, but this is just the revenue at x units minus 2x squared for the cost. So that's our profit function. So we're going to take the derivative. This is really just extreme value theorem problem. We're going to take the derivative. It's going to be 4x to the negative 1/2 minus 4x. And we can rewrite it as 4 over the square root of x minus 4x. And then we got to set equal to 0 and define. You could factor out the 4x to the negative 1/2 and just deal with exponents, or you could do this and combine them to a single fraction, which is what you should do. So this is x to the 3/2. And then, so x equals 0 is a critical point. And then we get a critical point from the top. So x equals 1, because you can take the 2/3 power of both sides, which does not give you plus or minus, because it's an odd root, it's cube root. So x equals 1 is so these are your critical points. And then there aren't necessarily endpoints. 0 would probably be an endpoint, but we don't have an upper endpoint, so we can't really do extreme value theorem. I mean, you could make a little table here and say, well, x and profit, and we plug 0 in and 1 in, and then do a limit as x goes to infinity to see what happens. So you plug 0 in here, you get 0. You plug 1 in here, you get 6. If you go to infinity, this is the dominant term, right? So it's going to go, profit is going to go to negative infinity. So, I mean, from this, you can say, oh, well, this is going to be the max. But you can't say extreme value theorem because it's not on a closed interval. I mean, I kind of used the idea of extreme value theorem with the table and stuff, but you don't have an endpoint, upper endpoint. So technically, you probably need to do like more of a first derivative test. But again, you're going to have to explain it like I did on the last problem. So you would do a line check with P prime, put your critical points on it. You would test a value, x equals, I don't know, pick something easy, like, well, P prime. Maybe something you know the square root of easily, like 4. So that would be 2. So P prime of 4 would be 2 minus 4 times 4 would be 16 minus 16. It's going to be negative, right? So it's going to be negative, positive, negative. So it's going down, up, down. Now, generally, this would not be good for trying to find absolute max or min because you have a relative max and a relative min, right? And that's not enough because the endpoints go down forever and up forever. But our domain, we do know that should be starting at 0. We shouldn't make negative things. And so in this case, it's going to become an absolute max. But the way you defend this answer is you can say, well, the profit has a relative maximum at x equals 0 units. No, x equals 1,000 units, right? By the way, 1,000 units. By the first derivative test for relative extrema. You shouldn't abbreviate these. You shouldn't initialize these. Use initials. First derivative test for relative extrema. And then you got to explain how it did that on that. Since P prime was positive on 0 to 1, and P prime was negative on x greater than 1. Okay. Since it is the only relative extrema on x greater than 0, it therefore must also be an absolute maximum. This should make you never want to use first derivative test for absolute maxes and mins. When possible. This one wasn't possible. So that'd be the way to do it. Okay, that's justification. Inscribing a cone, find the volume of the largest right circular cone that can be inscribed in a sphere. So you can imagine the sphere, the cone could be higher up. It could be like up here. Yeah, it could be way down here. Be kind of tall and skinny. And there's one that's going to have the biggest volume, but it's stuck inside this cone. So we got to work within this cone. So we're trying to largest volume. So we got to find the volume of a cone, which is 1/3 pi r squared h. This is the r down here, which we call x. The height is this whole thing. So the height would be y plus 3, right? Y plus 3. And so that's what we're going to plug in. So let's see. Volume of the cone is going to be 1/3 pi. R is x, and h is y plus 3. We're going to want to get this in terms of a single variable, and that's where its relationship to the sphere is going to, or whatever, is going to probably make a difference. We need to get one variable, all x's, all y's. I'm going to go with, you have a little right triangle right here, right? So x squared plus y squared equals 3 squared. So x squared equals 9 minus y squared, or, and that's what you could plug in here for the x squared, or you could do y squared equals 9 minus x squared. Take the square root of both sides. So it's up to you. I mean, this is attractive. I won't have any square roots and stuff. So, I mean, I would probably go that way. I'll do it both ways. So we'll do it the more traditional way first. Plus or minus, but we only want positive y's. Well, I guess, let's see. Could y be negative? Yeah, y would be negative if it was up here. So I guess we could entertain both possibilities. I guess I'm going to assume that further down here would be bigger. But let's see. Volume equals 1/3 pi x squared square root of 9 minus x squared plus 3. And then we'd want to probably distribute that, clean that up. So volume equals 1/3 pi x squared, square root of 9 minus x squared plus pi x squared. And so then I would take the derivative. This is a 1/2 power, so it's going to be 1/6 pi. We're going to have to do a product rule here, right? We have to do a product rule. So you could do derive this would be 2x, and then you leave that the same. Plus this other one should still have the 1/6 pi, or oh, hold on, that one would be 1/3 pi, right? Because I took the derivative of that one. This one's gonna be 1/6 pi x squared 9 minus x squared to the negative 1/2, and then you gotta do a chain rule. 2x negative 2x plus 2 pi x. That's ugly. That is ugly. So, and then you would set this equals 0 and define and solve it. So I'm not really into this one. I think I want to try the y. I mean, let's do that. Let's try that. I mean, you could go for that. Have fun. Otherwise, 1/3 pi, we could replace x squared with 9 minus y squared. And this looks like it's going to be a lot nicer. So 1/3 pi, 9y plus 27 minus y cubed minus 3y squared. We could rewrite this, go and distribute this. So this would be 3 pi y plus 9 pi minus pi y cubed over 3 minus y squared, pi y squared. So, I mean, it's still ugly, but it's not like the other one. So I think I like this. I'm going to try this. V prime would be 3 pi. That goes away. This one's going to be pi y squared minus 2 pi y. I'm going to set that equals 0 and define. And this one, let's see, I'm going to factor a negative pi out. Put the y squared first, and then the plus 2 pi y, and then the minus 3. I factored the pi out, so the pi shouldn't be there. Equals 0 undefined. Can I factor this? Y plus 3y minus 1. Yeah, I can factor that. You can do quadratic formula too. So we're going to get y equals negative 3 and y equals 1. I don't even want to know what it would be over with all those x's. This is way better. I bailed on the last one. So those are your critical points. And then your endpoints for y. Y could be as small as negative 3, I would say. Right? Negative 3, because then that's all the way up here, and the volume and the cone is all the way at the top, and y could be as much as positive 3, because then that would be all the way down here, and that would also result in a cone with no volume. But those are your endpoints. So like I've already demonstrated a couple times, I don't think you really want to do first derivative test, and this time we don't have to, so I wouldn't. I don't know what volume formula, maybe this one might be the easier one to use for calculations. So negative 3, 1, and 3. So if I plug negative 3 in here, I get 0. If I put positive 3, I get 0. If I plug 1 in, I get 1/3 pi, and that's going to be 8 times 4. So I get 32 pi over 3, and that's your max. There's a tie for the min of 0. So I would just go with that. The maximum volume is 32 pi over 3 cubic. What are the units? Oh, I guess there's no units. Units cubed when now we could find what x is. X equals the square root of that. 9 minus 1 square root of 8, or 2 root 2 units, and y equals 1 unit by extreme value theorem. Checking in points and critical points. So I need justification throughout this test for extreme values. And EVT is the way to go. I need the work and I need justification. So there you go. That was a little fun. Like I said, I bailed on the X, but you could keep going. Let me know how that goes, especially without a calculator. But let's see. Number 6 is a gravity problem. Now, at some point, I might have to stop this recording because I might run out of space and do a separate one just because it seems like it's going to be long. Robotics team launched a rocket at 45-degree angle at 64 root 2 feet per second. So I would draw a picture. So they're launching a rocket at a 45-degree angle, right? And it's going to go like that. It's two-dimensional motion. And so we get this right triangle here, 45, 45, 90. And this is the velocity. You got to break it down. So this is going to be 64 and 64. A lot of people made mistakes on the test in breaking down the components. So this is the velocity. This is the initial velocity. This is initial velocity in the x direction. This is initial velocity in the y direction. So what's the max height of the rocket? So I need EVT for this. So we should write our equations down. Now, this is on Earth, so the equation generally is y equals negative 1/2 gt squared plus vy naught t plus y naught. And x is going to be just vx naught t plus x naught, which we're probably just going to say is 0. And if they launch this from the ground, then that's going to be 0. And so our equation is going to be y equals, now g on Earth is negative 32 feet per second squared. And so that's why we get negative 16 t squared. Now, when I did another planet on the test that had, like, say, gravitational pull 12, you should have got a 6 here, negative 6. A lot of people didn't do the 1/2. There's a 1/2 here times g. G is negative 32 on Earth. That's why we get negative 16. Plus 64t. X is going to be 64t. We could find the velocity right now, negative 32t plus 64. We could find the acceleration. That's going to be negative 32, which makes sense on Earth. Okay, we need to find the time of impact. Okay, so impact is going to help us find our endpoints. So that's going to be when y equals 0. And so negative 16t, t minus 4. So we get t. You usually get 2 answers. A lot of times one doesn't make sense, but 0 makes sense at start at time 0. A lot of times if it started at initial height, you're going to get a negative time for impact. And of course, we're not going to use that. We need to find the critical point. So that's y prime, which is velocity, which I already wrote, negative 32t plus 64. We're going to set that equal to 0 undefined. And then we can factor it and get our critical point. Okay. So that's our critical point, and then we're going to make a table. So time and y. So it's going to be 0, 2, and 4. So if you plug 0 into y, you get 0. You plug 4 in, you should get 0. If you plug 2 in, you get negative 64 plus 128, you get 64. So this is your max. So you could say the maximum height is 64 feet at time t equals 2 seconds by extreme value theorem. Checking endpoints and critical points. Justification. Horizontal displacement. Well, that's going to be x at time of impact minus x initial time. Horizontal displacement. We're going to say that's 0, so we're going to just plug 4 into that. And so it's going to be 138, 276. No. 128, 256. 256. Show some more if we need to. Feet. Units. All right. Total distance traveled. You can use your graphing calculator for this. So total distance traveled, total distance in both directions is the integral of speed, just like it was last year for one-dimensional motion. But speed this year is the square root of vx squared plus vy squared. Now you need to show the setup. It's going to go from 0 to 4. So it's going to be 0 to 4. And for Vx, it's going to be just constant 64, right? Squared. And for Vy, it's going to be negative 32t plus 64 squared. And you write the dt. And then on your calculator, using your graphing calculator, you don't need to be in parametric mode. I would not be in that mode. I would just do math 8. No, sorry. Math 9. Math 9. We do square root 64 squared plus negative 32 plus 64 negative 32t. So we're going to put an x for all the t's. Plus 64, close parentheses, squared, close parentheses, comma x, comma 0, comma 4. So this should do it. That's it. 293.835 feet traveled, distance traveled. Velocity vector at time 1. So that just means we're going to plug 1 into the velocity for x, which is 64, and plug 1 in for y, which should give you 32. And so the velocity vector at time 1 is 64, comma 32. You always lead the x component first, and units are feet per second. The speed at time 1, well, the speed is going to be the square root of velocity at time 1 squared plus velocity of time y squared. And we just calculated those. That was 64 and 32. And I think we could pull this off without calculating it. What I would do is I'd pull a 32 squared out of both of those. And then you would have a 32 squared plus 1 left over. So you get 32. And then let's see, because 64 is 32 times 2 times 32 times 2. So actually there'd be a 2 squared left over. So this would be it. Your answer exactly would be 32.5 feet per second. Otherwise, if I let you use a calculator, you get the decimal for that and whatever, you know. Okay, parametrics and conics. So we want to recognize these different shapes. So we're using the trig identities, sine squared plus cosine squared equals 1. That's the one I've memorized very easily. And then if I divide everything by sine, I get another one. 1 plus cosine over sine is cotangent. 1 over sine is cosecant. Or I can divide everything by cosine squared, and I get tangent squared plus 1 equals secant squared. So you should be able to crank these out. The one we're going to use here is probably the one with secant and tan. So let's see here, secant 3 theta equals x minus 1 over 2, and tangent 3 theta equals y minus 2 over negative 3. So we're going to square those and plug those in. So I'm going to get y minus 2 over negative 3 all squared plus 1 equals x minus 1 over 2 all squared. So this looks like we're going to want a positive 1 over here. So I'm going to subtract this over this other side. So it's going to be x minus 1 squared over 4 minus y minus 2 squared over 9 equals 1. So that's my Cartesian equation, which I need to see in your work, and which will also help you graph it better. So the square root of what's on the bottom. So we got to get the shift. It's shifted up, right 1, up 2. So that's the center, right? Right 1, up 2. And then we're going to go left and right of that, 2 units, the square root of whatever's in the bottom. And we could make our graph better by maybe labeling them. And then we're going to go up or down 3. So we're up here at 5 now, and down 3. So we're down here at negative 3. So this one's at 1, negative 3. This one's at 1, 5. Okay, so then I'm going to create a box, whether I'm going to do a hyperbola or an ellipse. You could even do the boxes for circles. And something's wrong here. Up or down 3. I should have gone to here. So this should be 1, negative 1. This is a hyperbola, right? Hyperbola. I might write that down. And I want to see a sketch of the full shape, light sketch of the full shape. And it's either up or down or left or right, but because the x's are positive, it's going to be left and right. So we're going to sketch the whole thing, and then we're going to darken in what we need to. It should look like it's going towards the asymptotes and not crossing them or going back away from them later. Okay, so now this is where we're going to make a table and figure out what the x and y coordinates are, initial and terminal. So we're going to do pi over 3 and pi over 2, and then we've got to do 1 or 2 in the middle. Some of you guys didn't do it. I just took off points right away because I just think you either got lucky or you got it wrong because you didn't do it. So we could pick something nice in between. What you could do is give these guys a least common denominator of 6. And then this is 2 pi over 6, 3 pi over 6. So 4 pi over 6 would be a good in-between one, which is also 2 pi over 3. So if I plug in pi over 3 here, I get secant, which is 1 over cosine, right? Tangent sine over cosine. So cosine of pi is negative 1. So you're going to get 1 minus 2 is negative 1. And then for the y value, we're going to get sine of pi, which is 0. So that's just going to be 2. So negative 1, 2. This is your initial point, which I want labeled on your graph, at least that one with coordinates and labeled. So that's your initial point. And then pi over 2, if we plug that in, we get cosine of 3 pi over 2, which is 0. So we get 1 for this one. And then sine of 3 pi over 2, we get 2 minus 3. Sine of 3 pi over 2 is negative 1, but then cosine of 3 pi over 2 is 0. And so this one's actually undefined, which actually it means it's going to infinity, and I would say it's going towards a positive infinity because you have a negative and a negative here. So it's going to some kind of infinity. So that's going to be on one of those. Now you can't just, well, is it this one? Is it this one? Does it come in here? Does it go all the way through here? So that's why we need to do it in between points. So 2 pi over 3 would give you a cosine of 2 pi, which is, cosine of 2 pi is 1. So that's going to give you 3. And then sine of 2 pi is 0, so that's going to be 2. So 3 comma 2 is an in-between point here. So 3 comma 2, 3 comma 2. Okay, hold on a second. Is this really between these? Oh, no, I picked a bad point. 2 pi over 6 and 3 pi over 6. So we'd want to do maybe, we can make this is 2 pi over 6, and this is 3 pi over 6. So we could do these as over 12. It'd be 4 pi over 12, and this one would be 9 pi or 6 pi over 12. So I'm going to do my in-between points going to be 5 pi over 12. All right. So when I plug it in here, 3 times that, it's going to give me 5 pi over 4, which is root 2 over 2. So this is going to be 1 plus 2 times root 2 over 2. So that's going to be 1 plus root 2, which I'm going to estimate. That's about 1.7, so it's about 2.7. And then this one is going to be sine of 5 pi over 4 over cosine of 5 pi over 4. And that's going to be pi over 4, first quadrant. They're both going to be 1. It's going to be 2 minus 3 is negative 1. So this is what I'm going to graph in between points. So 2.7. 5 pi over 4. Okay. I don't know what I'm doing wrong here. Anyways, I feel like there's something wrong. Like this should be like negative or something. This is between these, right? 6 pi over 12. Well, I'm struggling here. Okay. Another point we could pick is potentially, we could do them like over 9 or something. This would be 4.5 pi over 9, and this would be 3 pi over 9. So 4 pi over 9 would be another point to possibly pick. The 5 pi over 12 should work though. So what am I doing wrong? I did it differently. I used 4 pi over 9 on my solutions. But I don't know. It's kind of weird. Okay, I'm going to try and finish this one right now. 5 pi over 12 be 5 pi over 4. Oh, 5 pi over 4 is actually in the third quadrant. And so that means that this is negative. So this should be minus. And so then this is going to be negative 1.7. Okay. And then in the third quadrant, they're both negative. So it does come. Okay. So now that's right. I was just doing my math wrong. So negative 1.7, negative 1 would be kind of like right there. So that confirms that this is the portion of your graph. And now this arrow doesn't indicate direction. This arrow indicates that it keeps going. So I need a second arrow to indicate direction. But that's it. That's your final thing. Now I'm going to stop this recording and do the last two problems in another one, just so I don't lose this.